Thank you very much for coming here and listening to my thoughts about geological sequestration of carbon dioxide. For some people refer it as carbon capture and storage. And initially, I just submitted the first line of this title, right? And there are a few ways how to present this topic. And then I thought, I decided to put as my personal experience, because I have approximately 20 years of dealing with this CCS technology. And in this way, probably put a little bit focus on challenges these technologies are facing. And the two topics I will briefly outline, and these topics are technical challenges. So there are some other challenges, of course, dealing with economic assessments or human dimensions. But I will avoid it in my topic if I can, although I may give some perspectives on those as well. So the first one is the feasibility of this technology to play a significant role on the reduction of emissions. Right? So some people think this is one of the technology which can play a big role, but there are some challenges, right? So I will try to outline those. And also the second one important is security of this technology, because I will tell you that the carbon dioxide, when injected underground, is less dense than residual fluids, and it has tendency to go up and find a way to leak back to the surface. If you Google the geological sequestration of carbon capture and storage, most likely you will see the following or similar pictures. So the idea is, so instead of venting it to the atmosphere, the carbon dioxide is captured from the source, for example, power plant, compressed to supercritical state, and injects deep underground. It's underground means more than 1,000 meters deep to keep the CO2 in supercritical state. And there are a few options to inject. So there are some depleted oil and gas reservoir when you produce hydrocarbons, and we have some porous space, porous volume to inject CO2. It could be some coal, a bed, a deep ocean, or saline aquifers. And the general consensus that, according to IPCC a few years ago, there is technical potential or capacity to inject approximately 2,000 gigaton of CO2. Gigaton is billion CO2. And in the current last year emissions of carbon dioxide is approximately 40 gigaton. So if you divide these two numbers, you can see that we have some time for this technology to play some roles of the reduction of emissions. So we have approximately order of magnitude of 100 years to still burn fossil fuels to produce energy and reduce emission by sequester this carbon underground. But this is kind of the rosy picture you can find elsewhere. But are we using this potential, right? So we have this capacity, technical capacity, but apparently it's not that easy to implement. And these are numbers. It's not my opinion. These are just solid numbers. And I will compare 20 years ago when I started this adventure of studying and developing those technology and what's happening now. So 20 years ago, it was approximately one operational project. There were a few of them, but this one is very famous, and it's called Sleipner CCS project in Norway. And they started to inject approximately 1 million ton per year. Right? So what's happening now is approximately 10 carbon capture and storage projects. So it's a little bit more, but some of the projects are already operational, some of them in the development stages. And the most solid number, so it's approximately 40 million tons per year, those projects are sequestered. So again, you can compare the numbers. So we have the 40 megaton per year we're storing now, and versus 40 gigaton or billion ton emissions we're having every year. Again, you divide those two numbers, and you can see that we are using only 0.1% of emissions. Right, so one can argue, does this technology works or not? But 0.1% is very small amount. Right, so we are not using the full potential. So most of the project have the design as we have one injection well, and the amount this well is injecting approximately 1 megaton per year. What is the future? How to scale it up? And there are two limiting cases. Do we need 1,000? I will just go back. So we have approximately 10 projects, and one of them is the Canada's shell sequestration project, Quest, name of Quest. So do we need to scale up and have 10,000 of projects like Quest, or we will have one Quest and multiple injectors? Right, so none of those limiting cases will work, right? So the reality, if we are going this way, will be somewhere in the middle. We would need 500, 1,000 projects, and the scale of those projects should be 10 to 20 megaton per year capacity. But in reality, the conditions of underground reservoirs, such as that one vertical well can inject approximately 1 megaton per year. So we will need to have each project to have multiple well scenarios. And then typically the lifetime of the power plant, 50 years. So let's play with those numbers. So if one well injects 1 million ton per year, and let's say we would like to project to have 20 million ton per year, one can do the math and say, no, we need 20 wells to inject this amount. But reality show, we worked on the other big sequestration project, which is called Waterloo Lake Sequestration Project. And we found out that when we try to inject this amount, trying to increase number of wells, we're not going this way of injection. So the capacity of multi-well scenario is much less. What happens when you start to inject, pressure builds up very quickly, and we cannot inject the fluid and exceed some fracture pressure. If you push strong enough, we will break the cap rock, and it's not allowed by regulation. So in reality, we found out that it's not that easy to inject fluid underground. Right? So imagine rock and you injection fluid like water or any other fluid into the rock. So it's not easy to do. When we first presented this result 15 years ago or so, it was a little bit surprising. People didn't expect this challenge to happen. So I'm currently one of my research activities trying to optimize the injection by placing well differently, changing the wells from vertical well, horizontal wells, doing some fracking in this well, and the options of increase this capacity or injectivity outlined on this slide. So the second topic, security, also is very important. As I mentioned already, the CO2 is less dense than, let's say, residual brine or some other fluids, and will try to escape from the formation. And this is the conventional the sequestration project. So you have porous media, have injection well, you inject CO2, and this is the plume in the green one, and this is schematics. After some time, this plume will try to occupy the top of the reservoir. It's less dense, it will find some ways to go out. So, to be able to inject underground, you need to satisfy a few criteria. So you need to, a very nice quality means not favorable capro to keep the CO2 in the reservoir. Also, another the problem that this CO2 will stay in this free phase for a long period of time, hundreds of thousands of years. Right? So what happens when the company or power plant which implement this technology is gone after 50 years? Who is going to assume responsibility for the future leakage? Right? So it's a very challenging task. So, and then also there are a limited amount of reservoirs which satisfy this criteria of nice capro. And then if we assume we have nice capro, it's still not guaranteed, right? So we don't have enough information what is underground. We need to collect somehow the input for our estimations. Also, unexpected finding we found during the practical implementation of this technology. What we found out, some reservoirs containing brine which has dissolved H2S. And we injecting CO2, so this initially dissolved H2S will be exiting of dissolved phase and becoming a free and buoyant phase. In the case we have leakage, we have not only CO2 leakage, but CO2 with H2S. And H2S is 1,000 times more toxic than CO2. So it's exactly true that people did know. And there are substantial amount of reservoirs which contain this H2S. And so this is another topic that we are also having research on. Also, by having these challenges, we realize that we can propose something new. So why don't we, instead of injection free-phase CO2, why don't we dissolve it on the surface and then inject it in the reservoir which already trapped, right? And so instead of injection CO2, we are taking brine from the reservoir, mixing this brine with the CO2, and then injecting this mixture into the reservoir. In this case, the CO2 is trapped and there is no risks of leakage. So, and then this technology allows to eliminate or substantially reduce the risk of leakage. First. The second is expand the range of underground formations available for storage. Right, so in this case, we don't have this requirement to have this capro, right? We can inject in any porous media as soon as already trapped. Of course, there are challenges. Nothing is for free, right? So the solubility of carbon dioxide in water is just few percent. So we need to have multiple amount of production wells, injection wells. It will be much more costly, right? But in the long run, it eliminates the risks of leakage. And there are challenges as well. And also, we developed some modeling how this carbon dioxide can be dissolved on the surface. It can be done on the surface pipeline, it can be done on the injection well, or it can be done in some other devices on the surface before injecting underground. And we thought it's a very reasonable time to dissolve CO2, which translates in some length of pipeline. So we found out we need just a few hundred meters of surface pipeline to achieve the complete dissolution of CO2 into the brine. And also it can be achieved in injection well. And I told you the injection well at least has 1,000 meters. to make it a supercritical state, so we can do it in injection well and achieve this dissolution. Right? So, and this is my last slide. If you are interested in my work, I have a bunch of application, all of this, the topics I presented, right? So you can send me an email, I can share the result of my research. Thank you very much.